All right, so we are going to move into section 3.3 and talk about graph sketching that goes along with asymptotes and rational functions. So not as much graphing in this section as there has been in the last couple, but there is one more big idea we have to go over, and that's the idea of different kinds of asymptotes. So let's look at what they're called, how they work, and then we'll do some examples. So first off, before we get into what an asymptote is and how you find it, when is an asymptote possible? Well, we are going to be working with what we call rational functions that you probably saw in an algebra class. Remember that a rational function is any function that can be described as f of x equals a function p divided by a function q, where p of x and q of x are polynomials and q of x cannot be zero. So essentially, you remember problems where you have x's on the top of the fraction, and x's on the bottom of your fraction. That is a rational function. The reason that the bottom of the function cannot equal zero is because we have to make sure we're careful about the domain. So the domain of f of x consists of all inputs of x for which q of x will not equal zero. When you have a function of this kind, you will probably have one, if not more, kinds of asymptotes. The first kind of asymptote I want to go over is called a vertical asymptote. So remember that a vertical asymptote has to mirror the image of a vertical line. So we're going to always write our answers as x equals the number a. And how you officially find that number a is the following. If you can take a left or right hand limit of a function at a certain number, and that number is what we're trying to find. If you can take a left or a right hand limit of an a value for a function, and you either get positive or negative infinity, that a value in which it happens is your vertical asymptote value. Now, doing it the limit way is very difficult, and that's not the way we're actually going to work these problems here, but that's the official definition. Down here at the bottom, here's more of a shorthand notation of how we're going to do this. Limits that approach positive or negative infinity will only occur where the denominator of the original function equals zero after simplifying. So what you're going to have to figure out is that what makes the bottom of your fraction, which is the denominator, what makes that equal zero? But the key here is you have to do it after simplifying. So in layman's terms, what you will do when they ask you for a vertical asymptote is you will take the function, you will simplify it by factoring or whatever techniques you have to do, and then you will set the bottom equal to zero. So let me show you how that works. So let's do 3 examples here. Example number 1. Determine the vertical asymptote or asymptotes, because there could be more than one, of the following function. If f of x is equal to x plus 4 divided by x minus 2, first thing you check for is, can you simplify this? Well, if you look at it, you can't factor the top of the bottom, and the top and our bottom don't have anything in common. So we checked that. So I'll kind of make this little note over here. Simplified? Yes. The function is as far simplified as you're going to make it. If that's the case, the only thing you have to do is take your denominator, which is x minus 2, and you're going to set that equal to 0. Solving this equation, if you add 2 to both sides, you will have an asymptote, or a vertical asymptote, of x equals 2. And you're done with this problem. Just make sure that on your assignments, when they ask about vertical asymptotes, that you write your answer as x equals the number. If you just type the number in, they may mark you wrong. So make sure you read your instructions and type it in the correct way. Let's look at a second example. So number 2, if f of x is 5x over x squared minus 25, what are the vertical asymptote or asymptotes? Well, on this one, there actually is some factoring that we can do. The 5x does not simplify, so I will leave that alone. But x squared minus 25 can be factored using difference of squares into x plus 5 times x minus 5. Now, even though this does factor, and I showed you that on the screen, you notice there's still nothing in common. There's nothing on top and bottom that can be canceled in like terms. So what that means now is, even though it doesn't simplify, you still need to set the bottom of this fraction. So x plus 5 times x minus 5 needs to equal 0. Now, just like when you did factoring back in an algebra class, when this is factored and it's equal to 0, you'll set both terms equal to 0 separately. If you solve them both, the first one, if you subtract 5 over, that would be x equals negative 5. And the second one, if you add 5 to both sides, you get x equals positive 5. So this is an example that actually has two vertical asymptotes in the problem. Now, the last one I want to show you, and I left a lot of extra room for a reason. This is an example where if you forget to simplify, you will mess up. Because the first two, we kind of got lucky. And even though if we had forgot to do the simplifying part, we would have got the right answers. On this one, let me show you what happens. If f of x is x plus 2 over x squared plus 6x plus 8, what is the vertical asymptotes? Well, in this example, once again, the numerator does not factor, so I'm going to leave that as x plus 2. But the denominator, which is x squared plus 6x plus 8, can be factored into x plus 2 times x plus 4. And as you can see, the top and the bottom both share an x plus 2 in common, so I can cancel this x plus 2 with this x plus 2 on the bottom. And since everything on the top goes away, that actually becomes an understood 1. And you now have a simplified function of 1 over x plus 4. Once your function is simplified, just take the denominator, which is x plus 4, and set that equal to 0. If you subtract the 4 over, you will get an answer of x equals negative 4. And that is your only vertical asymptote in this problem. This is a good example that if you forget to simplify, you will get the wrong answer every time. So please be careful when you're working on your assignments. Now, vertical asymptotes are not the only kind of asymptote you have to be able to find. There is another one called horizontal asymptote. And this is actually going to bring back an idea we covered in a previous section. I believe it was in section 1.5 when we did this, but don't quote me on that. We're going to review it anyways. So this is called a horizontal asymptote. First big difference you should notice is that when you write a horizontal asymptote, it's going to be of the form y equals b. So y equals this number b. It will be a horizontal asymptote if either of the following things are true. If you can take the negative infinite limit and get a b value, or if you can take a positive infinite limit and get a b value, this b value that you find is your value of the horizontal asymptote. And if I would just looked ahead a little bit now and not realize it was actually in section 1.2 when we did this. So I should have read a little bit ahead. So if you remember back in section 1.2, and you can go back in your notes and see where we did this, we covered how to do infinite limits. But since infinite limits also share the definition as a horizontal asymptote, we can actually calculate these very quickly by going over the two shortcuts we covered. So here we go. If you have a rational function, let's say f of x over g of x, and you want to take the infinite, and this also works for the negative infinite limit as well. If f of x, so if the power of f of x is greater than g of x, so if your top is greater than your bottom, then that means there is not a horizontal asymptote. That'll be the only time there's not one. If the power of f of x is less than g of x, so that means your top is less than your bottom, or you can read that as your bottom is bigger than your top, then your horizontal asymptote will always be y equals 0. And finally, the one you might have to do a little bit of work on, if the power of f of x and g of x are the same, so if your top equals your bottom, then the horizontal asymptote, if you remember, will be y equals the ratio of coefficients. And those ratio of coefficients come from the highest power on top and bottom of your function. So these go pretty quick because there's not really any work involved. There's just learning the rules. So let's run through some examples of how to find a horizontal asymptote. So number 4, if f of x is equal to 6x over 8x plus 3, what is the horizontal asymptote? Because if you're going to have one, you can only have one, unlike vertical where you can have more than one. When I do horizontal asymptotes, first thing I do is I'm going to kind of identify the highest power on top and bottom. And in this case, it's actually x. Since they match, this is rule 3, where you have to look at the ratio of coefficients. So if you look at the 6 on top and the 8 on the bottom, those are the coefficients that you're going to use. And we can say that y is equal to 6 over 8, which on your homework, they will require you to simplify that if it happens. They both share 2's in common. So this can be simplified into y equals 3/4. And that's your answer. That's it. Number 5 says, what if f of x is equal to 4x over x squared minus 3x? Well, if you look at the highest power on top and the highest power on the bottom, it's very easy to see that the power on the bottom is obviously greater than the power on top. That means you don't have to do any work here. This is rule number 2. Your answer is automatically y equals 0. So that would be your horizontal asymptote for number 5. Let's do a couple more. So number 6, what if f of x is equal to 4 plus 2 over x? Now this one you've got to be careful on, because technically how this function is set up, it doesn't follow any of our rules. This 4 here is causing an issue. So what you have to do before you apply your definitions is you've got to put these two things together by finding a common denominator. So what I'm going to do is, to make the denominators the same, I'm going to put an x below the 4, but to do that, I have to put an x on top to make it match. This will now give me 4x over x plus 2 over x. I can now put those together, and I have a new problem, which is 4x plus 2 divided by x. Now that it's one big fraction, I can use my horizontal asymptote rules that says find the highest power. Well, on the top and on the bottom, the highest power is an x. So we're going to look at our ratio of coefficients. There's a 4 on top. And even though you can't see a number on the bottom, it is understood to be 1. So if you divide those, we can say that our horizontal asymptote is y equals 4 divided by 1, which is just 4. So just be careful at the beginning. You can't use your rules unless the whole thing is one big fraction. Number 7, what if f of x is 4x plus 6x cubed divided by 3x squared minus x? So if you look for the highest power on top and bottom, the highest power on top is actually this x cubed, and the highest power on the bottom is actually this x squared. So in this example, your power on top is very easily seen to be bigger than the biggest power on the bottom. That's good news. This is rule number 1 that I showed you a few slides ago. If the top is bigger than the bottom, then there is no horizontal asymptote. Once again, that is only true if the power on top is bigger than the power on the bottom. All right, and then a little bit different idea. So instead of doing the rational function idea, let's talk about how you would do asymptotes of exponential and logarithmic functions. So we studied those back in chapter 2. These are actually a little bit easier because there's only a couple rules you have to know, and really it's just one rule for each kind. So let's begin with exponential functions. The good thing that is, if you work with an exponential function, and you can notice that both these rules are almost identical. If you can find an exponential function, you will always have a horizontal asymptote of y equals 0 every time. So unless there is some shift, and you can see that both of these functions, whichever rule you want to look at here, neither one of these has anything being added or subtracted. That would change your answer a little bit, but if it's just of the form a times e raised to the b times x, your horizontal asymptote will always be y equals 0 on both of these rules. The good news is that exponential functions don't have a vertical asymptote. Exponential functions only have a horizontal, so don't try to put a vertical answer in. Where this flips is when you move into a logarithmic function. And once again, a logarithmic function, while there are technically two rules, they both work very similarly. What it says is that if you have a function of the form, the natural log of x minus a, or the natural log of a minus x, it doesn't matter. Your vertical asymptote will always be x equals a. So you're noticing that logarithmic functions only have a vertical asymptote, and this vertical asymptote will occur at x equals a. Now, an easy way that I keep in mind of this is that whatever makes this equal to 0, or this one if it's written in the other form, whatever x value makes the inside 0, that is the number that's going to be for your vertical asymptote. And then just like exponentials, when you do logarithmics, I'm going to abbreviate here for a second, there is never, ever going to be a horizontal asymptote for a logarithmic function. So when you're working with these two special cases, exponentials, you only do horizontal, and it's always the same answer. Logarithmics always vertical, and you have to actually find that number, which we'll do in just a second. So we don't do a lot of these, so I'm not going to spend a lot of time doing a bunch of examples, but I did want to show you an example of each kind. So for example, number 8, determine the horizontal and or vertical asymptote of f of x equals the natural log of x plus 7. Now, since this is a natural log function, I know right away it has to be a vertical asymptote by definition. And then I'm asking myself, what number could I plug in for x here that would make the inside equal 0? And that would actually be a -7. So if you're writing your answer, remember a vertical asymptote is always x, and I know the number has to be -7. So my final answer here is x equals -7. And you can work that the exact same way for every natural log function. For number 9, it says find the asymptote that goes with f of x equals e to the 8x. Now, since this is an exponential function, I know that it's going to end up being a horizontal asymptote this time. And even better, if it's an exponential function, my horizontal asymptote is going to automatically be y equals 0. For the ones that we're going to do in this class, it's never going to be any different than that. So that should be a very simple answer when you see it on your homework and your quiz. All right, so I mentioned at the beginning of this video that there was only one graphing problem that you have to do, and this is it. So we're going to kind of combine everything we've learned from the last few sections into one big problem. So number 10 says, indicate where the function is increasing or decreasing. Do you have any relative extrema? Do you have any asymptotes? Where is the graph concave up or down? Do you have any inflection points? And then also, can you find any intercepts? When you're done, sketch the graph based on what you find. That's a lot of questions to answer. So we're going to take this one step at a time as we go through this. So the first thing I'm actually going to do, and I'm going to try to color coordinate this the best I can. I'm going to focus on asymptotes and intercepts first in blue. The reason I'm going to work on those is because they don't require calculus. You can do both of those based on the original function. So beginning with asymptotes, I'm going to abbreviate a little bit here. Let's start with the vertical asymptote. So remember when we did vertical asymptotes a little bit ago, you look at the original function and you ask yourself, can you simplify this? And the answer is no, this doesn't simplify. So all you have to do is take your denominator, which is x minus 5, and set that equal to 0. If I were to add the 5 over, you have your first answer. This graph has a vertical asymptote at x equals 5. For the horizontal asymptote, remember you're looking for the highest power on top or bottom. Well, in this case, the only x power you have is on the bottom. So therefore, if this says the bottom therefore has to be bigger than the top, because there isn't anything on the top to use. If your bottom is bigger than the top, then your horizontal asymptote is automatically y equals 0. And that takes care of our two asymptotes that we need. As far as intercepts go, if you remember from algebra, when you're asked to find an x-intercept, you're going to end up letting y equals 0. Now remember, f of x and y are the exact same thing. So if I let y be 0 in that original problem, I will have 0 equals a negative 2 over x minus 5. Now the problem is that if you try to solve this, so what some of y'all may try to do is that if I multiply both sides by x minus 5, while this does cancel, you run into an issue. This still gives you a 0 on the left, and you still have the negative 2 on the right. 0 never is going to equal negative 2. All of your x's actually end up canceling. Now, while that doesn't make sense in solving, here's what it means. It means that your graph has no x-intercepts. Let's see if the same can be said about a y-intercept. So remember, a y-intercept from algebra has a definition of x equals 0. So if I let x be 0 in the original problem, that would be y equals negative 2 over 0 minus 5, which ends up becoming negative 2 over negative 5, which is a positive 2/5. And since a y-intercept is just a point, I can write this as the point 0 2/5. So all of this stuff over here on the left of your screen, I did without taking a single derivative. All right, so now what stuff do you need calculus for? So I'm gonna move into red next. With the first derivative, if you remember back from 3.1, you can figure out where is the graph increasing or decreasing, and you can also find all of the relative extrema. So I need to take the first derivative of the function that we have. Now what I'm actually going to do here, I know I've done this with quotient rule in the past, but just to show you a different way of doing this, I'm actually going to think of this x minus 5 being raised to the first power, and I'm going to rewrite this as negative 2 times x minus 5 to the negative 1. That way I can apply the chain rule instead. So now back to red. If I want to find the first derivative of this function, negative 1 times negative 2 would be positive 2. I'm going to leave the inside alone. I'm going to subtract 1 from the power and then multiply by the derivative of the inside, which is 1. Now, if I were to clean this up a little bit, this would be 2 times x minus 5 to the negative second, which is the exact same thing as 2 over x minus 5 squared. Now, to find my critical values, remember when you have a fraction as your derivative, you have to ask yourself what makes the top and the bottom 0. Now, since there's not an x on top of this derivative, I'm not going to set the top equal to 0 because that's impossible. What I'm going to do is I'm just going to set the bottom equal to 0, and that will be my critical value. Now, we've solved a lot of problems like this, so to save a little bit of time, if you were to go through the process, you would end up find that 5 would be the only critical value of this problem. I am then going to draw a number line and plot 5 right in the middle. I'm going to pick out some test values. So how about I pick out 0 for the left-hand side and 6 for the right. And I'm going to plug both of those critical values into the first derivative. If you plug 0 into this, you should get a positive answer, which means that it's increasing to the left of 5. And if you plug 6 into the first derivative, you should also get a positive answer, which means you're also increasing to the right. Now, what I see some students mess up on this one is that they think if you're increasing on both sides, that means you're increasing everywhere. That's actually not true here, because if you remember from algebra, and the very first thing we found over here, there is a vertical asymptote at x equals 5. So that means, if you recall from algebra, your graph cannot cross a vertical asymptote. So while the sketch may look like it's increasing everywhere, technically, it is only increasing on both sides of 5. At x equals 5, there is a vertical asymptote, and thus nothing's happening. So you cannot write it as negative infinity to infinity, because technically that's not correct. Now, the one nice thing here, or two nice things, I guess, is that decreasing, it never does, because we didn't get any negative first derivatives. Also, extrema. Remember, for an extrema to be existing, for whether it be a max or a min, it has to alternate between increasing and decreasing. That never happens here, so there's not any. So you actually, the only thing we figured out from the first derivative is that you're going to be increasing on both sides of the vertical asymptote. Now, as I move to blue, we're now going to, or sorry, with the purple here, let's go to our second derivative stuff. That means, where is your graph concave up or concave down? And then, do you have any points of inflection? So over here, I'm going to rewrite my first derivative. So now I'm actually going to use this form because I want to do the chain rule again. So that was 2 times x minus 5 to the negative second. If I apply the chain rule here to find f double prime, negative 2 times 2 is negative 4. Leave the x minus 5 alone. Subtract by 1 to make it a negative third power. And then technically you are multiplying by 1 again. Well, this is the same thing as negative 4 times x minus 5 to the negative 3, which if I rewrite this, that is negative 4 over x minus 5 cubed. You need to find your candidates for a point of inflection like we did back in section 3.2. So technically you're going to set the top and the bottom equal to 0. But once again, there's no point in setting the top equal to 0 because negative 4 can't be 0. So I'm just going to set the x minus 5 cubed equal to 0. And once again, if you go through the algebra steps here, you should find the same x value we did a minute ago, because 5 is the only number that makes this equal 0. If I draw my number line and plot 5, I'm actually going to use the exact same two test values again. But remember, this time you are plugging them into the second derivative, not the first derivative. If I plug 0 into the second derivative, you should get a positive answer, which means you're concave up. Remember, we're doing second derivatives. If you plug 6 in, you will get a negative answer, which means you're concave down. So when I go to write my intervals of concavity, this is not the tricky part. You are going to be concave up from negative infinity to 5, and you're going to be concave down from 5 to infinity. As far as the point of inflection goes, I know we've always said that if your concavity switches, you have an inflection point. Technically, though, there's not one in this problem. Because once again, remember, at x equals 5, way back over here to step 1 of this problem, you have a vertical asymptote at x equals 5. So even though the concavity switches, that means you can't plot a point there, which means therefore you can't have a point of inflection. Now, from all of this, down here at the very bottom right of your screen, I'm going to draw a rough sketch of what's happening here. And let's do this, I guess we'll do it in red because that's the distinguishable color. On the far left, you have all of your asymptotes and intercepts that you can draw. So if I go to x equals 5, I can draw a vertical, I can draw a vertical asymptote, which, like I said, if you remember from algebra, is represented as a dotted line. Y equals 0 is actually the x-intercept, so we have an asymptote there. We don't have an x-intercept, and that kind of makes sense now because we have a horizontal asymptote there. And then at 0 2/5, which is about here, you have a y-intercept. The first derivative tells us that we have to be increasing everywhere, and the second derivative tells us that our concavity should go from concave up to concave down. So to the left of my vertical asymptote, I have to have a concave up increasing function. So that's going to look something like this. So as you can see, that graph is concave up and it is increasing. To the right of your vertical asymptote, you have to draw a concave down increasing function. So that's going to look something like this. You see that you are still increasing from left to right, but now you are concave down. This, while a lot of extra work, that's why we only do one of these. This is how you would go about finding all the information from a rational function that not only has asymptotes, but you have to do all the other stuff as well. All right, and then last but not least, I want to do a word problem to end this video on. So let's look at number 11 here. It says cities and companies find that the cost of pollution control increases along with percentage of pollutants being removed. Suppose that the cost in dollars of removing P% of pollutants from a chemical spill is given by C of P, which is 48,000 over 100 minus P. The graph of C of P is given. So it's down here on your screen now. I want you to do 3 things. Let's start with part A. I want you to find C of 0 and C of 80. Well, that's as simple as just plugging those numbers into the original function. So C of 0 is going to end up being 48,000 over 100 minus 0. And if I get my calculator out, I haven't used that today much. That's going to be 480. So what that means, and this is in money as well, this tells us that to get rid of none of the pollution, 0%, it would cost the city about $480. So what if you wanted to get rid of 80% of the pollution? So what if we did C of 80? Well, that would be 48,000 over 100 minus 80, which is the same thing as 48,000 over 20. That is going to be $2,400. So if you want to get rid of 80% of the pollution, you got to spend about $2,400. Part B, find the domain of C of P. So the domain would be what P values can you plug into this function. Now, if you look at 48,000 over 100 minus P, the domain, excuse me, has an issue because P cannot equal 100 on the bottom. Otherwise, that will give you a 0 and you can't divide by 0. Also keep in mind that you can't have a negative P value because you can't have negative pollution percentage, and you can't go over 100 because you can't remove more than 100% of the pollution. So if that's the case, if all of my numbers have to be between 0 and 100, my domain would actually be just 0 to 100. You can include the 0 because we plugged that number in, but you can't include the 100 because that would make a 0 on the bottom. So part C is the interesting one. Can the company or city afford to remove 100% of the pollutants due to this spill? Explain. Well, I'm going to explain this by looking at the graph. So as you get closer to 100% of the pollutants, so 100% would be right here on your graph. As you approach 100% of the pollutants, you will notice that your graph, sorry, one of my tabs is opened up by accident. Let me close this off. Go away. There it goes. Sorry. I don't know if y'all can see it, but one of my tabs actually opened up. As you approach 100%, look what's happening to your cost. It's quickly moving up. Now, I can't even see it on here, but when we got to 80%, we were at $2,400, and you can see the graph is still climbing. So in part C, when it says, can the company or city afford to remove this? The answer is no. Because the closer and closer you get to 100% of the pollution happening, you're getting closer and closer to your cost being exponentially high and thus for impossible to afford. The closer to 100, the way higher cost you have to spend. So the reason that is because since 100 does not exist on the bottom, there's probably, and I'm going to draw best I can, there's probably a vertical asymptote at x equals 100, or in this case, p equals 100. So that's what causes the giant rise in cost. So that ends the video on section 3.3. So that is all about vertical and horizontal asymptotes that we introduced. Starting in the next section, 3.4, we're going to move into a little bit different idea, kind of building ourselves up for word problems that are going to end this class.